Hey everyone, and welcome to today's Explainer. I am so thrilled you're joining me, because today we're going to completely reframe how we look at math. We so often get caught up thinking of mathematics as just numbers trapped on a page, right? Like abstract rules we just have to memorize for a test. But honestly, it's a highly practical, incredibly powerful language that we use to navigate the real world every single day. As we unpack the concepts from Chapter 12 today, we're going to explore 5 foundational tools from our everyday math toolkit. Because whether you're splitting a pizza with friends, figuring out if you have enough time to catch a flight, or just trying to organize your workspace, these concepts are literally always running in the background.
Okay, let's look at our roadmap for today. We've got a 5-part toolkit to get through. First up, subtracting whole numbers. Second, the art of estimation. Third, understanding and using fractions. Fourth, finding factors and multiples. And finally, mastering the 12-hour clock.
All right, let's just jump right in. Tool number 1, Section 1, Subtracting Whole Numbers, or Mechanics in Motion.
So, to really get a grip on subtraction, we have to look at its underlying logic. It's a simple 3-step scaffolding. You always start small and build up. First, you subtract the ones. Next, you move over and subtract the tens. And third, you subtract the hundreds. But here's where it gets interesting. What happens when the number you're subtracting from is just too small? Well, you have to borrow or carry over value from the next column to the left. It's basically a perfect little system of borrowing value to keep everything balanced.
Let's actually see this in action. Take a look at this example, where we're subtracting 1896 from 6753. Look at that ones column on the far right. You obviously can't take 6 away from 3. So what do? We borrow a 10 from the next column over, turning that 3 into a 13. 13 minus 6, that gives us 7. Awesome. But now in our tens column, our 5 has become a 4. We can't take 9 from 4, so we borrow from the hundreds, turning our 4 into a 14. 14 minus 9 is 5. We just continue this ripple effect all the way across until we hit our final answer, 4,857. Seeing it laid out like this really shows how 10 units from one place literally become 1 unit in the next column over.
Okay, moving right along to our second tool, Section 2, the art of estimation, visualizing the guesswork. Now, estimation gets a bit of a bad rap. A lot of people think it's just random guessing, but it's really not. It's actually a highly strategic approach to finding a close, reliable value when precise counting is either impossible or, let's face it, just totally impractical. It's all about using context clues to get an answer that is good enough for you to make a solid decision.
So, here's a question for you. How do you count what you can't even see? Imagine you had a certain amount of something. You gave a bunch of it away, and now you only know your starting number and what's sitting right there in front of you. How would you figure out the missing quantity without counting every single individual piece?
Well, we can use visual differences to figure that out in seconds. Check this out. On the left, we have a full bottle containing exactly 200 marbles. On the right, we see that exact same bottle after someone named Nimel gave most of his marbles away to his friends. Now, we absolutely do not have the time to sit there and count the remaining marbles one by one. But by just visually estimating, we can see the bottle on the right is only about a quarter or maybe a fifth full. So we can confidently estimate that he gave away somewhere around 150 to 160 marbles just by comparing the physical volume. It's such a quick, efficient mental shortcut.
All right, from estimating large groups to slicing things up perfectly. Section 3, understanding and using fractions.
Before we visualize this, we absolutely have to lock in the 2 foundational terms that make a fraction a fraction. First is the denominator. That's the bottom number. It tells us the total number of equal parts the whole unit has been divided into, the whole shebang. Second is the numerator, the top number. This tells us how many of those specific parts we're actually talking about. Think of it this way. The denominator is the whole book, and the numerator is the specific chapter we're reading.
And here is how that actually looks in the real world. Over on the left, a brother and sister want to share a guava equally. The whole guava is divided into 2 parts. That's our denominator. Each kid gets 1 part, our numerator. Boom! 1/2 each. Now on the right, we've got a cake being shared among 3 friends. Cut into 3 equal pieces, so our denominator is 3. Each friend gets 1 piece, so the numerator is 1. Everyone gets 1/3. It's mathematical fairness, guaranteed.
What we just looked at with the guava and the cake are what mathematicians call unit fractions. A unit fraction is just any proper fraction where the numerator is exactly 1. 1/2, 1/3, 1/4, you get the idea. These single-part slices are literally the building blocks for all other complex fractions. Think about it.
If you have 2/3 of a cake, you really just have 2 of those 1/3 unit fractions mashed together.
Okay, on to Section 4, Finding Factors and Multiples. We just looked at breaking a single item down. Now we're going to look at grouping whole numbers together.
Imagine for a second you're setting up a room and you need to arrange 6 chairs. You could put them all in one long single row of 6. Or you could set up 2 rows with 3 chairs in each. In both of those scenarios, 1 times 6 equals 6 and 2 times 3 equals 6. You are hitting the exact same total quantity, but you're getting there by multiplying entirely different sets of whole numbers.
Take a look at all the physical combinations for organizing those chairs. We've got 1 row of 6, 2 rows of 3, 3 rows of 2, and even 6 rows of 1. By physically moving these chairs around, we're actually proving a mathematical rule. 1, 2, 3, and 6 are all numbers that divide evenly into 6, and because of that, they are all considered factors of 6.
So the cool thing is that any whole number can be broken down into its foundational factors, like this. Let's take a slightly bigger number, like 12. You find its factors by hunting down every single whole number pair that multiplies together to create it. So 1 times 12, 2 times 6, 3 times 4. This means the complete list of factors for 12 is 1, 2, 3, 4, 6, and 12. Honestly, it's kind of like discovering the DNA of a number. It tells you exactly what that number is built from.
And that brings us to Section 5, our final and arguably most practical tool, mastering the 12-hour clock.
Okay, we have all stared at an analog clock on the wall at some point. But here's the catch. A full day is 24 hours long, right? But our standard clocks only have 12 numbers. That means that little hour hand has to do 2 full laps every single day. Look at these 2 images. Both clocks show exactly 7 o'clock. But the image on the left is a student heading out the door for morning school, while the one on the right is a student studying under a lamp in the evening. Because 7 o'clock happens twice a day, we desperately need a system so we don't mix them up.
And that system actually comes to us straight from ancient Latin. We basically chop the day right down the middle, at noon. The 12-hour block from midnight to noon is called ante meridiem, which literally translates to before midday. We just shorten that to AM. The second block, from noon all the way until midnight, is post meridiem, or after midday, which we shorten to PM. Locking those terms in is absolutely crucial so you don't accidentally set your morning alarm for dinner time.
And this is exactly why knowing this stuff matters on a global scale. Check out this flight schedule from an international airport. If you're flying to New Delhi, your ticket might say 7:15 p.m. But aviation and international systems, they almost always use the standard 24-hour clock to completely eliminate any of that AM-PM confusion. In standard form, 7:15 p.m. just becomes 19:15. You literally just add 12 hours to any PM time. Seamlessly converting between the 12-hour clock we use in conversation and the 24-hour clock the world runs on is just a massive game changer for navigating modern life.
Well, we've covered a ton of ground today unpacking this everyday math toolkit, from the mechanics of subtracting and carrying over values to the strategic art of estimating. We've sliced things up into unit fractions, found the DNA of numbers using factors, and finally structured our days around the 12-hour clock. Like I said at the beginning, math isn't just stuck on a chalkboard. It's happening all around you every single second. So as you go about the rest of your day, I want to leave you with this. Which of these mathematical tools are you unknowingly using right now? And how will you use them to navigate your world tomorrow? Keep looking for the numbers, keep learning, and I'll catch you on the next explainer.